Hey everybody, this is Matt with Camping and Coding, and today we're going to be going over the daily Leetcode problem for Saturday, July 11th, 2026. Okay, so this problem is a graph traversal problem. We're given an integer n. There's an undirected graph that has n vertices numbered 0 to n minus 1. We're given a 2D integer array edges where each internal array denotes that there is an edge between the two elements of that array, and they want us to return the number of complete connected components of the graph. So a connected component is a subgraph of a graph in which there exists a path between any two vertices and no vertex of the subgraph shares an edge with a vertex outside of the subgraph. A connected component is said to be complete if there exists an edge between every pair of its vertices. So looking at these examples, 5 is a complete connected graph because it's in isolation. So is 0, 1, 2 because every node is connected to every other node and it is not connected to any node outside of that subgraph. So too with nodes 3 and 4. Okay, so it is pretty obvious that this is going to be a graph traversal problem. As with all graph problems, we have a variety of algorithms we can use. Here we are just looking to count the connected components with a little extra added step of making sure that the component is complete. So this is going to be a breadth-first search algorithm. And we're going to do that with a queue and with an adjacency list. Okay, so we'll do some boilerplate here just to get things started. So from collections, import default dict and deck. Call our class solution, and we'll define our function count complete components. Whenever we have a function inside a class, we need to have self as the first argument. We've been told we'll have an integer n and edges, which is a list of lists of ints. And again, that just represents the edges in the graph. Okay. And we're going to return an integer. All right, so we know that we need to return the number of complete subgraphs. So we'll start there. All right, and this is a breadth-first search problem, like I mentioned. So we're going to use a queue. In Python, I like to use a deck to represent a queue, which is just a double-ended queue because it allows for append left, append, and pop. So it's very convenient for queue type problems, also for stack problems, but that's not the case here. Okay, so as with most graph traversal problems, especially when we're talking about depth-first search or breadth-first search, there's some boilerplate that we almost always need. So one of those things is a way to represent whether or not we've visited a node. We need this so that we don't just endlessly iterate over the nodes. So the way I like to represent this, and especially in a problem like this where we're given the number of nodes n, I just have an array that's a Boolean and we know the length, so we can just give it length n. So this initializes visited array to false for every node. Okay, we also need a way to check all of the nodes that are connected to each node. So if you think about this in the graph, if we are starting at node 0, we know that we are going to need to check node 1 because it's connected to node 0, as well as node 2 because it's connected to node 0. It is also connected to node 1 and vice versa. So if we were to just do this iteratively using the edges array, we would wind up exploding our runtime, and that's not something we want to do. So one efficient way to represent a graph like this is with an adjacency list. So that just means we have an entry for every node, and then so the key for each is each node, and the value is an array that represents all of the nodes that share an edge with that original node. So we'll do an adjacency list. It'll be from our collections. Default dict is nice because you don't have to worry about checking for existence of a key before you insert something. So if we were just to do, for example, edgelist equals a regular dictionary, this would be fine, but we would need to do a check like if 0 is not in edge list, then edge list at 0 is equal to an empty list or whatever. I don't want to do that. It's a lot of boilerplate that I don't care about, and I don't want to write it every time. So we'll just do a default dict, which allows us to just initialize on the fly. It's another handy Python convention. Okay, so we are going to say for every edge in our edges array, I want to say our adjacency list at the first node in the edges array is going to be a list of nodes that that node is connected to. And so we only know for this one edge that that is the second element. Now, this is an undirected graph, so we need to handle the opposite direction as well. So we have an adjacency list here for, say, node 0 that will show it's connected to 1 and 2, but we also need to represent that 1 is connected to 0 and 2 is connected to 0. So we need to have our adjacency list, edge 1. Okay, so that covers both directions. All right, now we need to iterate over all of our nodes in our subgraph. One way to do this would be to iterate over all of our edges, but there's an immediate problem here, which is that some nodes can be isolated, like 5 here, and it has no entry in edges, so we would skip that completely and our solution would be wrong. So we are instead going to iterate over every single node, which I'm going to call a vertex here. So for v in range n, we know that there are n minus 1 nodes, and so we'll just iterate over all of them. Okay, so I'm going to start with just the breadth first search component of this, and that will give us a way to count the connected components, and then I will add some of the other. Well, I'll just start with the breadth first search generically, and then we'll talk about how to add the connected components. Okay, so in general, if you're interested in the breadth first search, you want to use a queue because you want to know for each vertex at a given level what is it connected to, and explore all of those before you continue down the rest of the graph. So for example, we start with 0. We want to explore 0, 1, and 2 before we move on to any other subgraph. So that is exactly what we're going to do here. So we only want to check a node if it's been visited, which means, if it's not been visited. So at the very beginning here, we want to say if a node is not visited, then we want to start the breadth first search process. So we'll initialize a queue, which for us today is going to be a deck. And we're just going to append our first vertex. Now, importantly, we need to immediately mark that vertex as visited because we don't want to ever visit this again, or else we're going to wind up throwing off our numbers with duplicate entries. Okay, so now we're checking everything around our first vertex here, vertex V. So in this case, that would be 0. We want to check 1 and 2. Now, our Q is going to represent what is connected to vertex 0. And so we are going to say while our Q is not empty, we're going to select the first one. Pop left removes the leftmost element from the queue and assigns it if there's an assignment operation happening. Okay, and then we're going to say for each neighbor that's in the adjacency list for that specific node, the one that we just popped off the queue, we want to say if that neighbor has not been visited, append it to our queue. So in our example here, we're at 0. Our first neighbor is 1 in our adjacency list. We haven't visited that yet, so we want to add it to our queue so we explore its neighbors as well. So we append the neighbor and we immediately mark it as visited. Okay. And now you've done a breadth-first search. It's really that simple. If you walk through this algorithm, you will see that this explores every single vertex and all of its neighbors, and it does it really efficiently. It's big O of V plus E, so the number of vertices plus the number of edges. And so this is a really efficient way to traverse the entire graph, exploring fully one connected region before you move to the next. Okay, but we need to do something else here. We need to keep track of whether or not these are complete connected subgraphs, not just traverse over them. Okay, so if we were to run our tests just with the breadth first search solution here, we would fail. Actually, we're failing because I didn't import collections before using it. Okay, let's try that again. Right. Okay, so as expected, we are failing everything. And that's because we're doing a breadth first search here, but we're not actually checking for graph completeness. So a complete graph means that every node is connected to every other node in that subgraph. So for us, we want to make sure that for every subgraph, for example, 0, 1, 2, it is complete. So 0 is connected to 1, and 0 is connected to 2, 1 is connected to 0, 1 is connected to 2, 2 is connected to 0, and 2 is connected to 1. So that's a complete graph. Every node is connected to every other node. Okay, so there's probably a way to do this that involves checking all of these things to make sure that they are all connected to each other. That is not what I want to do. That sounds very painful. So instead, I am just going to count the number of edges and the number of nodes in each subgraph. So we'll call the number of nodes in each subgraph K and the number of edges E in each subgraph. So we need to know and keep track of how many edges we've encountered, or how many nodes we've encountered, and how many edges exist between those. And then we can do some math and find out if the number of edges is the correct number of edges for a complete graph. Okay, so we are visiting a node, and at that point we need to record that we visited it. So we'll increment our number of nodes, and then we need to figure out where to increment the number of edges. So we know that well, let's think about a couple of options. One is that we could check when we get the current node, right? We could do e plus equals 1. That's one option. This is not going to be correct because that is incrementing the number of edges when we're just looking at the node. So that would mean when we pop off 0, it would increment edges. But then when we pop off 1, it would increment edges again. And so we would just wind up with edges equal to k, and that's not what we care about. So we're not going to do that. Okay, so what's another option? We could say count every neighbor in our adjacency list. Remember, our adjacency list is representing something like we have, say, node 0, and it is adjacent, that is connected to 1 and 2 in this case. So 0 is connected to 1 and 2, and 1 is connected to 0 and 2, and 2 is connected to 0 and 1, and then 3 is connected to 4, is connected to 4, 4 is connected to 3, and 5. Now, here's an interesting question. Does 5 appear in our adjacency list? Well, it doesn't have an edge because it's not connected to anything. So no, it does not. And this is why it was important for us to iterate over the vertices rather than the adjacency list or the edges or something like that. So we can either unconditionally add an edge when we pop off or when we visit a neighbor here, or we can do it only when we visit it. Let's do it unconditionally because we need to account for the neighbor. This is an undirected graph. We need to account for the neighbor when we first see it from 0 to 1, but also when we see it from 2 to 1, and it would not be accounted for. So if we think about when we pop off 0, if we conditionally incremented the number of edges, when we pop off 0, we would get 0 to 1, that's good. We would also get 0 to 2, that's good. And that happens as we iterate over the neighbors in the adjacency list. But then when we pop off 1, we would not get the 1 to 0 edge or the 1 to 2 edge, which is okay for the 1 to 0 edge because we already accounted for that in 0 to 1, but we would never get the 1 to 2 edge, and that's a big problem because we would be undercounting. So we don't want this to be conditional. We want this to be unconditional. When we visit each neighbor, we count the number of edges. Okay. So if we were to walk through just a simple example here, this 0, 1, 2 subgraph, we are going to be counting the number of edges every time we visit a node. So we'll count 0 to 1 and 0 to 2, and then when we pop off 1, we'll count 1 to 0 and 1 to 2, and when we pop off 2, we'll count 2 to 0 and 2 to 1. So we are double counting here, which is okay because we are always double counting, which means we can just say that E, we can say that E is equal to E integer division 2. So basically this is just a floor division operation, so that's fine. Okay, so now we have E set to what we want it to be. Now we need to check, I guess, what is the relationship that we expect between the number of nodes and the number of edges in a complete graph? In a complete graph, the number of edges is equal to the number of nodes. The number of edges is equal to the number of nodes times the number of nodes minus minus 1, all of that divided by 2. In this case, we're dividing by 2, and that's because this is an undirected graph. So for the same reason we divided by 2 for the edges here, we are dividing by 2 when we compute the expected number of edges. So for us, this will just be, this will tell us whether the graph is complete or not, the subgraph. So we say if E is equal to k times k minus 1, all of that divided by 2. Okay, then we want to increment complete. Okay, I think this is right. Let's find out. No, this is not right because I have a typo. Okay, let's try again. Okay, let's run these tests. Interesting. We are failing 15 of the tests. It looks like we are undercounting something here. Undercounting the number for not visited. Oh, okay. So we're counting the edges correctly. We are not counting the nodes correctly. Let's try this again. There we go. Okay, 26 tests pass. That's great. That was a little messy. Hopefully me making mistakes here on my own was useful to you. I should also mention that I did not import typing, or I didn't import list from typing. So just to be safe, import typing from typing, import list. The reason I did that is because I happen to be using Python 3.14 here, but in older versions of Python, this will probably fail at compile time. This is inferred in Python 3.14, but not in older versions. So importing typing and then using the list type is the safest way. So let's just make sure we're still running. We are. That's great. Hopefully this was helpful. If you have any questions, drop them in the comments. Thanks for watching.